In this presentation, we will see the working of JK flip-flop. You have already studied about the SR flip-flop and D flip-flop. So what is the need to study the next type of flip-flop, that is your third flip-flop? There must be some disadvantage in SR and D flip-flop. That's why we have to move to the JK flip-flop. And first of all, we will see what is that advantage that we are getting from the JK flip-flop. Then we will see the working of your JK flip-flop. So in D flip-flop, you already know that there is a single input, that is D. We call it the data input, and hence two possible combinations. But in SR flip-flop, I have made the truth table for SR flip-flop because we will use it for your JK flip-flop. And in this you can see there are two inputs and hence four possible combinations when your clock is high. So it is always good to have a 4 combinations as compared to 2 combinations, but there is one disadvantage in this. The last combination, when S is 1 and R is 1, is a not used state, so we don't use it. Okay, there is a contradiction that you have already seen in the SR flip-flop. So in this whole presentation, what we will try to do, we will try to make a flip-flop in which this 1 state is used. There is some usable form when we are having S as 1 and R as 1, and the flip-flop obtained is called as the JK flip-flop. So I hope it is now clear that why we have to study the JK flip-flop. Now let's move to the circuit for the JK flip-flop. This is the circuit for SR flip-flop, and we will try to make a JK flip-flop from this circuit only. Okay, so let's see what changes we have to do to get a JK flip-flop. There are two outputs to this, Q and Q complement. I will take Q from here, okay, and I will give this Q as one of the input to our NAND gate, the NAND gate in which R is one of the input. Similarly, I will take Q complement out and give it to the NAND gate in which S is acting as one of the input, like this. Okay, so this is our JK flip-flop. Okay, now I will write S as J and R as K. The next thing is the working of this flip-flop. So the first case is when clock is low, and you already know in this circuit when clock is low, at this point I'm having 1, and at this point also I'm having 1, and this is your NAND latch, NAND SR latch, you already know. And whenever the input to the NAND SR latch is 1 1, the output is stored, so I will call it memory state. Okay, very simple. The next thing is when clock is high and your J is 1 and K is 0. So there will be no change if you compare the truth table for SR flip-flop and JK flip-flop. The outputs are going to be same. So our Q is 1 and Q complement is 0. From here you can see. Now I will see the third case when clock is 1, our J is 0 and K is 1. Now from the SR truth table you can see that the value for output, that is your Q, is 0 and Q complement is 1. So till now you have seen that for the first 4 cases everything is same in JK flip-flop and SR flip-flop, but this last case is different and very important, so let's discuss it. In this, my clock is high, my J is 1 and my K is also 1. So what will be the values for your Q and Q complement, that we have to see. So before actually writing the values down, we have to do the analysis in this circuit, and for that I will assume Q as 0 and Q complement as 1. So let's write it down. Q is 0 and Q complement is 1. Now you can see that Q is given as one of the input to this gate and the value of Q is 0. So here I am having 0. My K is 1, you can see, so K is 1. Clock is also 1 always, and the Q complement is given as the input to this NAND gate and it is 1. So at this point I'm having 1, S is 1, clock is 1 again. Now we know how to operate with the NAND gate. First we have to take the AND operation for the 3 inputs, and then we have to complement it. So 1 and 1 and 1 is 1, and when we take the complement I'm having 0. So at this point I'm having 0, and 1 and 1 and 0 is 0. Taking the complement gives us 1. So for the NAND SR latch, I'm having inputs as 0 and 1, and you very well know that when this happens, the output is 1, 0. Okay, now you can see that the output is changed, so the input will also change. Q has become 1, so at this point instead of 0 I'm having 1. Q complement has become 0, so 1 will become 0 here. Now 1 and 1 and 1 will give us 1, and taking its complement I'm having 0 here, and 0 and 1 is 0, and taking its complement gives us 1. So this 0 will become 1. Now when this happens, we are having output as 0, 1. Similarly, if you do the analysis once again, you will find that at this point I'm having 1, this is 0, it will become 0 again, and it will become 1 again, and Q will be 1, Q complement will be 0. So there is one pattern you can see. The Q is changing from 0 to 1, 1 to 0, 0 to 1. It is actually racing very fast. So I can write it like Q is 0, 1, 0, 1 and so on. Q complement is 1, 0, 1, 0 and so on. It is racing, and a very important concept in the digital electronics. Let me write it down, important, because we are going to use it directly in our counters. And now what will be the output when this happens? You can see that when Q was 0, it will become 1, and when it is 1, it will become 0. So if I say Qn plus 1, that is my output here. If it is 0, it will become now 1, and again it will become 0. So it is actually the complement of the previous state. So whatever be the value for the Qn, we are having output as Qn complement. So this not used state is now Qn complement. This is we call as the toggling. There is difference between the toggling and racing that I will explain separately in one presentation. So this is all for this presentation, a very important one, and you have to remember this truth table. There is a slight difference from the SR truth table, in which the last state gives us Qn complement. We will use it for our excitation table and characteristic table in the next presentation. So see you in the next presentation. In this presentation, I will talk about the preset and clear inputs in flip-flops. They are very important because I will use them in the counters. So let's start with them. They are the direct inputs or overriding inputs or asynchronous inputs. I am calling them the overriding inputs because whenever they come in picture, they will change the output. The Qn will be changed directly. It will not see what is the value of SNR, what is the value of clock. It is changed, and it will give a predefined value whenever this preset and clear inputs come in the picture. Therefore I am calling it the overriding inputs. I will tell you how they are changing the outputs, but before that let me tell you what is the asynchronous and synchronous inputs. Asynchronous is preset and clear, whereas synchronous is SR, JK, D and T. You have to keep this thing in your mind. Now this is my SR flip-flop, and I will show you where we have to put the preset and where we have to put the clear input. The preset input will go here. This is my preset input, and my clear input will go to this NAND gate. This is clear. Now let us see, when preset is 0, what will happen to the output. If it is 0, the output here will always be 1, so Qn will be 1 always. Now when clear is 0, the output here will be 1, and Qn complement is always 1, which means Qn is 0. So we have to see for Qn, it is 1 as soon as preset will become 0, and it will become 0 as soon as clear will become 0. So let me write this thing down. Preset equals to 0 implies that Qn is equal to 1. I just explained it here. And when clear is equal to 0, Qn becomes 0 because Qn complement is 1 in that case. So this is important thing that you have to keep in your mind, and let me write one important thing here. Qn is equal to 1 and Qn is equal to 0 when preset is 0 and clear is 0, and it will not see what is the value of S, R, J, K, D and T, or whatever be the value of clock. It is going to give this output. So whatever be the value of clock and synchronous inputs, you can write this thing with these cases. The next thing is the block diagram of this whole setup, how it looks. This is the flip-flop, SR, the clock, two outputs, Qn complement, and the preset will be given here with this bubble. It shows that it is active low signal. Whenever it is low, the output will be generated, and whenever clear is low, the output will also be generated. So we put bubble here to show that it is an active low signal, and this is the representation with preset and clear inputs. Now we will see the truth table, in which the inputs are preset, clear, output is Qn, the two variables, thus we are having 4 combinations, 0 1 1 0 1 1. Now let's see what will be the output depending upon these conditions. When preset is 0, clear is 0. It means there is a contradiction. You can see from here, when preset is 0, Qn is 1, and when clear is 0, Qn is 0. So at the same time they are compelling the Qn to become 1 and 0. Therefore it is not used. When preset is 0, Qn is 1, and when clear is 1, it means at this point we are having 0. So the clear has no impact on the circuit, and also you can see when clear is 1, we are having an AND gate, so the output is not affected at all. So Qn is 1 from here. Similarly, when preset is 1, clear is 0, Qn is 0 because preset has no impact on the circuit, whereas clear will make the Qn equals to 0. When both of them are 1 1, it means the flip-flop will perform normally. Okay, from here you can see that when preset is 1, clear is 1, we are having 0 0. They are not going to change anything in the circuit. And also we can see from this circuit, when preset is 1 and clear is 1, they are not going to affect the value of this NAND gate. So this is all that you need to know about the preset and the clear inputs. We are going to use this preset and clear directly for the designing of the counters. That's why it is important to know these things at this point. So this is all for this presentation. In the last two presentations, we completed the JK flip-flop from its working to different tables involved in it. And if you remember, when we were discussing the JK flip-flop, I told you that we used JK flip-flop because there was some disadvantages in your D and SR flip-flop. In SR flip-flop, you already know that when S is 1 and R is 1, the output is unpredictable. We don't use that. So to overcome this disadvantage, we use JK flip-flop, and it is possible because of this feedback that you can see in purple color. But there was one problem in JK flip-flop also, that when J is 1, K is 1 and clock is 1, we are having something called as the race around condition. The output starts racing, that we will see in a minute. And if you really want to use JK flip-flop, you have to overcome this condition. So in this presentation, we are going to find out this race around condition, and we will see what are the different methods involved in the elimination of this particular condition. It's a very important presentation, and from this presentation only you will know the use of your master slave flip-flops. So let's move to our circuit without wasting any time. You already know this 4 combinations, that how the output has been written. This Qn plus 1 is nothing but your Q, and this Qn plus 1 complement is Q complement. I have just generalized it, and I have written it as Qn plus 1. You can also write it as Qn, and this as Qn complement, but this thing will then change to Qn minus 1 qn minus 1, and similarly this will qn minus 1 complement and qn minus 1 complement. There's nothing special in the name, you just have to know the concepts. I'm not going to explain these 4 combinations, you already know it. We will just see this last combination and try to find out the values for qn plus 1 and qn plus 1 complement. So let's move to our circuit. J is 1, k is 1, and our clock is also high. Now I will say q is 1 and q complement is 0. I have just assumed these values, and as you can see that q is one of the input to this NAND gate, so at this point also I'm having 1, and q complement is input to this NAND gate, so at this point I'm having 0. Now these 3 inputs are given to this NAND gate and these 3 inputs are given to this NAND gate, and it's very simple to determine the value of these 2 NAND gates. 0 and 1 is 0, and we have to take the complement, so I'm having 1 at this point. 1 and 1 is 1, and taking its complement I'm having 0. Now this circuit is very much familiar to you. It is your SR NAND latch, and you already know that when SR NAND latch is involved and the inputs are 1 and 0, the output will be 0, 1. Now you will find that the inputs changed. Q has become 0, so instead of 1 I am having 0 now, and Q complement has become 1, so instead of 0 I am having 1 now. Now 1 and 1 is 1, and taking its complement we are having 0. Similarly this will change to 1, and the output will now 1, 0. So again the outputs are switched from 0 to 1 and 1 to 0. So we are having 0 and 1, and this 0 will become 1 and this 1 will become 0. So again output has switched from 1 to 0 and 0 to 1. So this particular condition, when your output is changing from 1 to 0 and again 1 then 0 continuously, we call it as race around condition. Remember, there is a difference between toggling and race around condition. Toggle is controlled, but race around condition is not controlled, and we are trying to make this toggle. Okay, this race around condition needed to be converted in the toggling condition that we can use in our different circuits, and it is directly used in your counters. So this is something we call as race around condition. And if I draw this condition with my clock, so let's see how it looks. First of all, I will have my J, and J is 1 always, and then my K, and K is also 1, because for race around condition J and K must be 1. But you can see that the race around condition is only when the clock is high. So the race around condition will be for this period, for this period, for this one, and for this one. So let's see what will be my output Qn plus 1. Okay, now it will be low because the clock is 0, and I'm assuming that previous state was 0, and once clock is 1 it will become high from 0 to 1, and again it will become low, then it goes high, then low, and it repeats this process of racing and continue to do this till the clock becomes low. Now the clock is low, it will be low, and again it starts racing when the clock is high. So this particular condition is our racing, and there are different ways to overcome this condition. So you have to remember 2 things for your race around condition. This is your racing, okay, and it will be possible only when J is equal to 1, K is equal to 1, and your clock is high. There is another point also that you have to keep in your mind, is that the clock's half time period, this is the time period of your clock, and the half time period, that is T by 2, must be greater than the delay of your flip-flop. Okay, because if the delay is greater than your half time period, the clock will be low and the output will not be generated. By delay I mean that once you have changed the inputs and made the clock high, these gates require their own time to generate the output. Okay, they will not generate output instantaneously, but they require little bit of time for their own process. Let's say if q is 1 and q complement is 0, and for getting q as 0 and q complement as 1, we need to wait for a certain time. Let's say it is t dash. The t dash is the time taken by this flip-flop to generate the output. Then this t dash must be greater than the half time period of the clock. Okay, because this circuit will be operational only when the clock is high. Let's see what are the conditions to overcome deracing. So conditions to overcome racing. Okay, so let's first talk about this thing. When I explained that why the half time period of the clock must be greater than the propagation delay of the flip-flop to attain the racing. Okay, but we don't want racing, so what we will do, we will make the half time period of clock less than the propagation delay of our flip-flop. So this is the first condition by which we can overcome deracing. Now we will talk about the second way to overcome deracing. In this way, instead of using the level triggering, we will use the edge triggering. You already know we are having two types of edge triggering. The first one is your positive edge triggering and the second one is your negative edge triggering. So you can see when we are having edge triggering, there is not enough time for the circuit to race. So this is our second way to overcome the deracing. And the third way is master slave, and it is very important condition at the same time. This master slave condition is the most popular condition to overcome deracing, and it is widely used. There are so many advantages of this particular circuit, and we will see in the next presentation how to operate with JK master slave. It's a very interesting topic. One more thing at the end of this presentation I want to ask from you people. I really want feedback from your side, that what you like about my lectures and what you don't like. I just want to know that whether my speed is too slow or it is too fast, my pronunciation, my pitch, whatever you want to suggest, you can suggest. I will try to modify my lectures on it. So please do that. It will help you and also others. So thank you for watching. See you in the next presentation. In the last presentation, we completed racing or race around condition in JK flip-flop. I explained you how our output is changing in this manner that we call as the racing, and racing is definitely not a desired output. We don't use racing in anything. So what we use toggling. And the difference between toggling and racing is that racing is an uncontrolled phenomena, whereas the toggling is controlled. So we are having some ways by which we can have toggling out of the racing condition. The first one that I told you was keeping the clock half time period, that is t by 2, less than the propagation delay of our flip-flop. But let me tell you one thing, that this particular method to overcome the racing is not practical and it is not used. So what we are left with, the second method, that is our edge triggering, and definitely it is used. And the third one and the most important one is the master slave operation that we are going to discuss in this presentation. And this master slave operation is same as the negative edge triggering. So let me write this important point so that you may remember this thing. The master slave operation is same as negative edge triggered flip-flop. I will explain this thing in one of my presentations. When we are having our clock and a circuit depending upon some outputs, we will see how the negative edge triggered flip-flop is same as our master slave flip-flop. It is a very important point to remember, and it helps some time to solve the multiple choice questions. So keep this thing in your mind. Now let's move to our master slave operation. Here you can see a JK flip-flop. A simple JK flip-flop is here with the feedbacks, and the racing is because of this feedback only. So we have to design something so that we can eliminate the effect of this feedback. So what we are going to do, we have to add another stage. By another stage I mean we have to add another circuit like this. So let's do it. It will be clear in a minute. So I need to remove this feedback. So let's do it first. Okay, now the feedback is removed and we have to add one more stage. So I have already copied it down. Let me paste it. This is our one more stage. Okay, now let us connect the output to the input of the second stage like this. And now let us connect the feedback to the output of this stage. So what we have done, instead of having this input to this gate from here, the output of the first stage, we have connected the feedback to the output of the second stage. So this is an important thing in a master-slave flip-flop. There are basically two things you have to remember in master-slave flip-flop. The first thing is this feedback, that how to connect the feedback. And the second important thing is the clock. You can see a clock has been given to this stage, and also there is a slot for a clock for this stage. But instead of having the clock directly given to this stage, we will complement it first. So we will add a NOT gate here. And now this is the second important point in the master-slave operation, and this circuit we call as the master-slave circuit. It can be implemented for SR as well as D flip-flop. There is no problem in doing that, but in this presentation we are going to discuss for JK flip-flop. So what is the effect of complementing the clock? Let's see. For example, if J is 1, K is 1 and clock is high, so what will happen? This first stage, these are actually the two flip-flops. This one is my flip-flop 1, this one is my flip-flop 2, and this flip-flop I call as the master. So let me write it down. This flip-flop I call as the master, and this flip-flop I called as the slave, and because of this thing only they are called as the master slave. Now I will explain you why it is called as master and why it is called as slave. It all depends upon the clock, because when clock is high, this master is operational, but as the clock is complemented and given to the slave will not be operational. It will keep the memory. So we are having our output QM changed, and the output Q remains the same because the clock is low when the clock is high for the master. Similarly, when the clock is low, the clock will high for the slave, and master will not be functional whereas the slave will be functional, and the output changes. But there is one interesting thing going on, that when this output changes, we are having feedback here, but the clock is low, therefore this master is not operational, so there is no effect of feedback. We have eliminated the effect of feedback and hence the racing. So what actually is happening in this circuit is that instead of output changing continuously from 1 to 0, the output changes once in a clock cycle. This is the advantage of this circuit, and that is called as the toggling. For better understanding, we have to make a clock and we have to see for our outputs QM and Q. So let's make our clock first. The clock is changing as a function of time, and the values for J and K are 1 throughout. Okay, so this is my clock. This is low, this is high, and CLOCK. Now we will see what is the value of QM for this. So this is my QM. I will extend this line so that we can plot our outputs in a correct manner. So let me do it first. Okay, this much will work. Now we will plot QM. When clock is high, it means the master is operational while the slave is not. So when the master is operational, and I assume that QM was low before the clock is high, so as soon as the clock is high, the QM will become high also because it was low earlier. Okay, and for what time it will be high? It will be high for this entire time, because when the clock becomes low, the state will be stored, and the state was high, so it will be stored like this. And again, when the clock is high, it will become low like this, and then high. So you can say that for a clock cycle we are having the toggling. Okay, it is high, then it is low. This can be used directly. Now we will try to find out our Q, that is the output of our slave, and let's see what we are having. When the clock is high, it means that the master is operational but the slave is not, because we are complementing the clock. So here I am having a 0. So if 0 was the output previously, I am having a 0 stored till the clock is high, and when the clock is low, 0 here, I am having 1 here. It means the slave is operational. So it will go high and it will remain high until the clock again became low. So low and then high. So this is what we are having as the output of our master and output of our slave, and you can clearly see that we have overcome this racing. The output is not changing continuously from 0 to 1, but it is changing once in a cycle. That's we call as the toggling. So if I write the value for our output when J and K and our clock is high, the output Qn plus 1 will be Qn complement. This we call as the toggling, and it is used in the counters. So I hope you understand now what is master slave operation in JK flip-flop. It's a very simple thing. You can also do it for the D flip-flop, and this is all for this presentation. In the next presentation we will try to understand the operation of the T flip-flop. So see you in the next one.